Hey, hello everyone, and welcome to week 7 of the tutorials, or the tutorial session for week 7 of MechMed Hacks on Transformers. Our mentors today, Nicole and Charmy, will go over the notebook, Google Colab notebook, that explains, like a little bit of the coding behind Transformers and uses it in a simple example. So from this, I'll just like hand it off to Charmy and Nicole, and yeah, you guys take it over. Thank you so much.
So I guess we can start with a bit of self-introduction, so you guys can know us a little bit more. So I'll start off. I'm Nicole, and I'm Nicole Zhang. So I am a MD PhD student at McGill, and who is also doing work at Mila. So my work is mainly focused on generative modeling. So I'm sure you have all heard about diffusion models. And so one of the things I'm working on is using conditional flow matching, which is another kind of framework to do diffusion modeling. And so for me, I am looking forward to something that's more jointly medicine and AI in the future. So I'll probably have my own lab and so on. And so yeah, that's about me.
Great. And I'm Charmy. I recently finished my master's in machine learning from University of Montreal and Mila. Last year, I interned with AWS in Vancouver on the false annotation detection task. I have experience working with document AI field where we extract data out of documents and standardize them in a particular format. And I'm also an international speaker and I love community work and engaging with people. So do reach out to me if you need any help for NLP or CV related tasks. And today, I believe we will start first of all with Nicole. She will walk us through the first half of the collab. And in the later part, I will talk about how to use or fine tune VIT for a classification task using Hugging Face. Thank you.
Okay, so I'm going to share my screen and you guys can tell me if you can see it.
Yes, we can.
Great, thank you. So Transformers, it's initially really used for NLP purposes, which is reflected in the original paper if you have, tried to read it, called Attention is All You Need. If you haven't, it's linked here. And so initially it was working on language translations and it performed better than the state-of-the-art model then. And now it has been adapted to other tasks such as vision, reinforcement learning. So it's quite a powerful framework. And so why transformers? Transformers kind of fill the niche that's previously RNN, the recurrent neural network, and the convolutional neural network has kind of fall short on for certain tasks. So one thing that it can really do is it can model long range dependencies in sequences. And so due to this ability, it's quite valuable for certain tasks that needs kind of spatial resolution or kind of memory of the past events. It can also accommodate long sequences. So this is kind of helped with positional encoding, in which that, whatever sequences that you kind of have, it's all kind of condensed into the same kind of embedding hyperspace. As well, you have training that can be parallelized. That's unlike RNN. And so one thing about machine learning is how well a model can scale. And so transformers can really scale, of course, with a lot of compute powers. That's why it's very popular. And so we can kind of take a look at the architecture. So here we can see that the input is kind of processed the same way as the outputs, but the outputs is shifted right compared to the input. And so you first have this embedding in which that you encode words or pictures into this space. And then you do this positional encoding to also encode their relative positions to each other. And so here you have kind of multiples of this multi-head attention and feed-forward block, in which that afterwards the output gets fed into this block with the output, and then you have whatever task that you want to do. And so let's just start with something like positional encoding, which is what the workshop talked about. And so this snippet of code is directly from the workshop. And if you try to run it, you can see that this is basically a function that's plotting the heat map of the positional encoding. And you can see that the 512 is basically how much dimension they have, and you can see it's the y-axis here, and then the x-axis is the length that's being encoded, which is 100. And so the color corresponds to the number, and you can see that there is kind of a differing color gradient across, and then it falls off kind of here. And so this is basically what the model will see once you input something into it. It will see, those kind of numbers represented by the positions. And so if you look at the original paper, they have the positional encoding as something that's not learnable, but it's very straightforward. It's basically like a transformation using sine and cosine from the positions. And so, there's something that you can really try, which is I wrote kind of a very rudimentary encoding function here, which only have dimension of 1 compared to the dimension of 512 here. And so, if you want to try, you can kind of change this function up to see to see how you can make this, instead of just one number throughout the dimensions, make it different kind of numbers in terms of the encoding, so that it would look something more like this. And so I guess I can throw this question out there if someone wants to answer, which is, why do we need so many dimensions in terms of the encoding? Why don't we just have one dimension instead of 512 dimensions as this function has? And sometimes, you can have even more. And so, you can think about that. I can also give you the answer later. But basically, in short, you want this function to have more dimensions to accommodate more words. So think about how many words there are in even just the English language. And so that's basically, the whole dictionary, and that's a lot. And so, you sometimes have very, very long sentences that you really want to encode. And it's best to have more dimensions to accommodate this length than shorter. So hence the 512. But if you manage to change it up, you will see something that's more like this. And so this is after you change the positional encoding to match, which is kind of the hint, what you are supposed to encode. And then this heat map is what you will get in the end. And so this is what the model will see when you input, for example, those 100 words. This is the first word, second word, third word, and so on. And so this is essentially the input. And so now we can look into some of the basics about the transformers. So how to load the pre-trained model, tokenize the input, and look at the output from the model. And so here the question to have kind of 3 parts. So based on the example provided in the workshop, and you can read the documentation here, which is, if you click it, it will take you to the transformers documentation. And you can see that here are all the kind of models that you can use that's pre-trained, because training those models take a lot of resources. So, if you can, you probably should just use some of those that's pre-trained. So if we try to find BERT, this is the one that we are kind of looking for. You can look at how to what it looks like, what you can load from this kind of library. And one thing that's very important is to learn to use those libraries and how to load them and understand them. And so here, you can basically follow this, which is you prepare the run by installing the relevant things in, for example, transformers, data sets, and here the Colab will basically do it for you. And if you're running it locally, then you can just really do it once and it's done. And afterwards, you can basically, load the transformers, the BERT model, and also you can specify which BERT model you want, and then you can print the model config to see what it approximately looks like, because sometimes the model can be fairly big and it's hard to visualize what they're doing under the hood. So that will kind of help you in terms of what the model kind of feels like. And here we define our sentence, hello transformer models. And we want to tokenize the sentence. And so we use the BERT tokenizer, and we tokenize this, and then we print the tokens. And so you can hear after you download the model, the config for the model, you basically have all those things that's describing the model. And you can see the version, the size, the hidden size, and what kind of activation function it has. And so after you tokenize the sentence, you can see that here, this is kind of how they are broken down. So, instead of hello transformer models, they break down each of the syntax, each of the word, and the different kind of ending, and also the punctuations. And so afterwards, this is what you are inputting into the model. So it's very important to understand what you are actually inputting. So you know exactly what the model is seeing, and then it will also help you debug in the future. So here you can see there are 1, 2, 3, 4, 5, 6 kind of things. But, in reality, you have something that's more than that, basically. So if you really tokenize the sentence and then you encode it, you can see that there are more words. That's because there are different kind of encoders that will encode this sentence into kind of this hyperspace here. And so this is it has like 8 kind of dimensions. So it's a 1x8 matrix. And now you can try to pass the input tensors through the model and examine the output from the model. And so this is fairly straightforward. You can always play around with it however you like. And here we're using the input tensor into the output, and then we're printing the output. And you can see here it's a very big matrix of the pooling layer, and as well as the hidden layers. And so if you want to look kind of more in detail of what they are like and their size, which is basically the dimension of the matrix, the output. And you can see that the model will give you 2 outputs. One is the last hidden state, in which that you can see it's 1x8 by 768. And so the 8 here, if you think about it, it corresponds to the encoding here. So each of the encoding is converted to the state. And then the Pooler output is basically the representation of this whole sentence in the space. So if we think about what this can be used, there are certain things like sentence classification, name entity recognition, and semantic similarities. And so, it's something that you can think about is for all of those applications above, what kind of input you would kind of prioritize or use for those kind of things. So sentence classification. And the answer is here. Obviously, you can take a look at it and try to see if this makes sense to you. And so there's also the transformers for medical imaging. It's basically, I think, at the end, if we have time to kind of talk about it, but this is basically the first part of basic transformers and using transformers from kind of existing libraries. Is there any questions? If there is not, then we can probably move on to the second part. Okay, well, you can always message me later. So I think that's probably your section now, Charmy.
Sure. So let me share my screen now. Yes, I hope my screen is visible to everyone. And so here, at the end of this notebook, I have given the link to the answers of all the questions that we are gonna see over here. So I'm directly opening that notebook today. In this entire part 2 of today's tutorial, we are gonna build a vision transformer for the image classification task. The way we are using convolution neural networks in other classes or an other deep learning approach, after the introduction of transformers, people started initially, transformers were built for the text related task, and it was initially built for the text translation task. But after that, people thought, how about applying them on images? So Vision Transformer by Google Brain is one such initiative, and it's basically a BERT, but applied to images. The way we have characters and combination of characters as a words and a phrase and a sequence, similarly, we can see an image as pixels or a combination of patches. So instead of applying an entire image, if we patch here in this example, we are taking 9 patches of the images, and each of this patch contains a sequence of a lot of pixels. If we apply those pixels to a transformer function and then try to get a classification that if this image is of a bird or a ball or a car or what, we will be able to get an answer pretty quickly and with good accuracy. So today, the dataset that we are going to use is CIFAR-10 dataset, which is a collection of 60,000 images of 32 cross 32 is the dimension. There are 10 different classes, and in total, there are 6,000 images per class. So there is no class imbalance or any such issues. I have run this notebook already because of size of the data set, and training the model is a bit time consuming, but it is pretty straightforward that first of all, we have to install the transformer and the data sets. The CIFAR-10 data set that we are going to use is part of the library. So we are not supposed to wget from any other external link, but we can simply use from datasets, import the dataset, namely CIFAR-10. As I mentioned, it consists of 60,000 images, but just for the sake of this demoing purpose, I have taken the first 5,000 images in the training class and the first 2,000 images for the test class. And after all of the 5,000 images in the train class that we have, we will split it into training set and validation set. And that is simply done by using the train test split function. And here we can mention that what is the validation data set size that we want to give. Here 0.1 means 10%. So out of all the 5,000 images that we have in the train set, we are going to use the 10%, which is the first 500 images, as our validation set. So here we can print the length of the training data set, the validation, and the test set. And if we want to just print what is the structure of this train DS, so in the dataset class, it has features. Each of these features has some image and label. We will see later on what that exactly means. And in total, there are 4500 rows. So now, out of all of these features, which contains images and labels. So images, this PIL type of an image, which is containing all of the pixel and the image metadata. And in the labels, since we have 10 different classes for this data set, we will be having 10 names, namely airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So all the images that we have in the data set are of these classes, and whatever testing we will do, the model is supposed to give us an answer from this 10 different classes. The first very simple question that I had asked in the tutorial notebook, that how do we visualize these images? So it's a very simple one-liner code that get your train data set and fix any of the index that you want to print it, and it'll just display you that what is that image. And if you want to print the corresponding label, we can also access the label feature of that. But now what exactly is this 3 represent? So for that, we are simply gonna use ID to label and label to ID, those two dictionaries that we will also use later on in the code. So from all the labels.names, I'm just enumerating the IDs and the label and creating a dictionary. So from now here, we can see that the third index or the third label is for cat, and hence this image is of cat or a dog. So here I have used the index 10. So it is a cat. Now, as Nicole mentioned earlier, that for the text class, if we use a text data set, what we need to do is tokenize them and pre-process them. Similarly, the way we use the Hugging Face tokenizer function to tokenize the text data, we will use the image processor inside of Transformers class to pre-process the data on the go. This line will first of all download that for us. And after that, the next part is the data augmentation. Similar to all the other image processing tasks, or maybe the way we do in CNN, that if we have a limited amount of data set, or we want to make our model robust enough, what should we do? We can apply a lot of image data augmentation strategies like normalizing it or centering through the image, considering the center part and cropping it, resizing it, or randomly resizing, and lots of other things that we can do over here. So first of all, we are importing that what all different kinds of transforms that we want to apply to our images. And once we apply to our training images, we also have to do the same thing for the test images before evaluating our model. So here we have, first of all, normalize the image, and then we are applying the horizontal flip to our image and randomized crop. And then we are just converting this image data to tensors. So the horizontal flip just means that taking a mirror image of your original image, so as to make the model robust. Same thing we are doing for the validation and for training. And the next question in the notebook that I had asked is, how do we have created this train transform and well transforms, but how do we apply them to all the images of our data set? So it's pretty simple, that the examples parameter that we are getting over here, that consists a list of lots of images. So for each of the images inside this examples, we simply need to transform, and whatever output that we get, we will just put it in a list to get the examples pixel value. But we cannot just simply pass this image. If you have tried that code, you might have a certain error that those images are not of the same compatible form. So that's why the simple thing that we can do is to convert this image to RGB form and then simply apply the train transform. The same thing we will apply for the validation transform. And here now all the images that we have in the training data set and in our validation data set, we have applied the transformer. We can also see that the data that we now have is like an image, which is a PIL form of size 32 cross 32, and it's in RGB form now. Whatever the label of that is, here I have printed the first two, or if we just want to print the very first thing, then we will see that that is one image. This is the label of this image, and this is the pixel values of that image after applying the transforms. And that is the simple thing now that we need to do is before now defining our model and running the model, all the data set that we have, the way we wanted for the model inputs, we will use the data loader to convert them. So the pixel values and the labels that we have in our train DS and in our validation DS for each of the images, we will just use the simple data loader to pass that entire thing, and we will initialize the batch size. So what is the batch size that we want to use for our train loader that we can define over here? I guess the default is 8, and it's up to you, whatever number that you wanna use over here. And here we can see that since we are using the batch size as 4, now the torch dot size is 4. That is the number of the images in a particular batch is, and this is the dimension. This is like RGB 3 channels that we have. That's why this number is 3. And that is the dimension of the image that we have since very beginning. So those are the number of rows and number of columns. And particular label for here is 4. Okay, the bad part is now ending very quickly. So we loaded the data set, we transformed the data set, and we had the data loader. Everything that was pretty tricky, but now defining the model, running the model, evaluating the model is always very easy. In the next 5 to 10 lines of the code, we will be having an entire classification model built using VIT that can run on the CFAR dataset. What we have to do, first of all, let's get the model from Hugging Face. So for that, we are using the VIT for image classification. And this is the particular Hugging Face model that we are using. There are tons of other variants as well. And if you want to try something else, feel free to do it. You just need to change this one string value. And from the Hugging Face library, if you want to use any other image transformer classification kind of a model, you can use it easily. And just to have the mapping between the label name and label index, we are just passing this ID to label and label to ID parameters. And once we have downloaded the pre-trained model, what we do is, first of all, define the training arguments. So there can be tons of training arguments and all these hyperparameters that you can set and tune. But for set of this tutorial, what we are gonna do is using the most important and most frequently used parameters. First of all, this is the folder where we want to save the model checkpoints. And if you have run this function, you can see that once you will run over here. So this test CFAR 10 is the folder name which it will create. And inside that, it will create a lot of different checkpoints. And how would it save this checkpoints is by the save strategy. And here we are mentioning that we want to use the save strategies as epoch. So after a certain epoch has ended, we want to save the model parameters or the model checkpoint at that stage. So the optimizer.pt file and scheduler.pt and everything has been saved in this folder after the end of each epoch. We have run this for 3 epochs. That means we have 3 different folders containing all of this information. And after we have finished one epoch of our training procedure that we want to do the evaluation again. And since we are saving on each epoch, we are also doing the evaluation at each epoch. Here is a learning rate 2e⁻⁵. You can tune it to other learning rates and see how is the accuracy and the training validation loss are increasing or decreasing. Per device training batch size, here we are using the GPU of Google Colab. And for that, how many number of batch sizes that we want to pass in one go that we can set over here. This is the default 8. You can change it according to your hardware. And then we can mention the number of epochs, what the weight decay that we want to do. And here it's a nice thing that load best model at the end we are setting to true. What does it mean is we have trained our model for 3 epochs, but it can happen that the best accuracy of a model is giving is at the very first epoch, and after both the epochs the accuracy is decreasing somehow. So here the load best model at the end will do is that for the entire epochs, the entire training that we have done, at whatever epoch we got the best accuracy, we will load that particular model at the end to do the final evaluation, to print any graphs. In this case, we will have a confusion matrix. So for that, we will just use the best model that we have so far. Metric name we have initialized as accuracy over here. So the evaluation we will do is based on the accuracy equation. And this is just simply the logging the logs to the logs dir that you can see over here. And remove unused columns. If you have some kind of data set that you want to remove your unused columns, you can do it. But in this case, I have mentioned over here as well that we are setting it to false because we do not want to remove any of the images columns that we have. So now the next question in the tutorial was to build your own compute matrix. And how would you do it? So simply we can use the sklearn's accuracy score, and whatever the prediction that we have versus the original labels that we have. So this is the predicted label, this is the original label, and we are passing it to the accuracy score, and simply returning it will give us the accuracy of a particular data set or at end of this epoch. And here we are setting excess is 1 because we want to see column wise column that which of the out of this 10 labels, which label has the max accuracy for this image. So let's say I have an image of a cat, and in the output for this, since this is a multi-class classification problem, there are 10 different classes. Each of the classes will have some number as an output that model thinks, is this a cat, is this a dog, is this a deer, and so on. So we want to get the maximum, the argmax. So we want to get the maximum number of model prediction probability that we will use it for the accuracy score function. And now we have the training arguments ready. We have the compute matrix ready. What we can now do is just simply use a trainer, pass it the model. The model is here that we downloaded from Hugging Face. So pass the model, pass the training arguments, and all the training data set, validation data set, and compute matrix, and then trainer.train. And after a while, it took like 8 minutes and 50 seconds for me to run this first 3 epochs. And as we can see, the accuracy is increasing from 94% to 95.8% after the end of the second epoch. But here it is now stagnant. So it's the same, but as we can see that the validation loss is decreasing from 0.48 to 0.41. And now to evaluate the model is also pretty simple. The way we do trainer.train, we can do trainer.predict, and then all the test data set that we have. And if we pass it to our trainer.predict, we will get the outputs. In the output, we will get a lot of different information, that what is the test loss, what is the test accuracy, the runtime, the samples this model is processing per second, and so on. And the final question and the final portion of today's tutorial, that once you have your outputs on the test data set, how do we evaluate that, how the model is performing? So one strategy is to make a confusion matrix. And what confusion matrix sees is, since we have the 10 labels, it's a multi-class classification problem. The confusion matrix will be of size 10 cross 10. Here we have the true labels, all the 10, and here we have the predicted labels. And over the diagonal, we can see that there is a high numbers. What it means is that if for a particular image, if the true label was airplane, and if the model predicted airplane, we will increment the counter for this particular thing. Then we will go again for automobile. If a particular image was of automobile, that was a true label and model predicted also, then that is fine. But what this one represent is that the true label was automobile, but the model predicted it as airplane. So this is a wrong prediction, but all of these are right predictions. And if we have higher diagonal values, then that is good, that our model is predicting pretty well. Since our test accuracy is like 97%, which is pretty good, hence we can see high values over the diagonal. And finally, it's a very straightforward code to get the confusion matrix, which is a kind of a tabular or a matrix form. We should have y true and y predicted, and for all the outputs that we have, we can get the y true and y pred for that. And here I'm using just training data set to just get the names, like all of this 10 names that you are seeing over here. So we are reading it from the label of this features and passing the y true and y pred to the confusion matrix, and what are the colors and text and rotation, that fancy things if you want to set over here, then you can just plot it. So that is it, from using the data set to transforming the data set and then passing all the arguments and having a good classification using Hugging Face and VIT transformer. So I hope it's pretty clear now, and I would like to know if you have any questions on this or from the first part which Nicole took, and let us know if you have any questions.
Cool. Thank you so much, Nicole and Charmy. It was really nice presentation. I know I'm gonna be watching this like multiple times as well, like when I'm going through the stuff for transformers. Let's hear the audience. So does any of the audience have like a question? If not, we can probably then end the session today. So I'm going to stop recording. And obviously, like if there's any question, just put it on Discord or email us, and then the mentors will like send a message to the mentors. And yeah, that's it. Thank you all. We'll be in touch. Bye.